Alright, we're going to talk about structures. Hopefully you've seen them a little bit by this point, but we'll talk about how to create them, talk about how to use memory, talk about how to manipulate them in a variety of ways. Um, so we'll use these later, so you can kind of ignore the code up here to begin with. We're just going to dive into part one right here. So uh, like normally you'd see something here, like int, whatever the variable name is. And between 71, 72, and 73, those are the same type of creation. So we're creating a data type. Line 72, you're creating a data type of an integer. In this new line 72 that we have right here, we're creating a data type called student. So you've never seen, a student data type before. Student data type was created in this code itself. So if we go up here, this is how you create a structure called student. In this case, we're using typedef. So you can do a typedef, which will define everything after typedef to fit this name. So we're creating a structure. This is the main code of how to create a structure right here. And you're creating a structure with a first name, a last name, a student ID, credits attempted, credits earned, quality points, all that inside of it. So a structure will just contain all this in one big, essentially chunk in memory. So you can use it, and all these pieces of data are attached to each other by name, essentially. You can also put a structure inside a structure. So in this case, I made a structure called student billing. And inside billing, I just, quick amount owed, amount paid, scholarship, stuff like that. Same thing up here. So later on, when we're talking about structures, we talk about the other ways to make them. Kind of the default way to make them is here, where you say struct and then give it a name, and then you can put whatever you want inside of it, similar to what we just saw. And it's a great way to keep things organized. But when you make it this way, if you wanted to make a variable of that data type that we just made, you'd have to do this. So similar to what we just did with int hello, if you wanted to make a data type using struct example, you'd have to actually type out struct again. Just the way the default definition of how to create a structure is, this is what you'd have to do to make each data type. And you could do the same thing you've always done, that you can put them on multiple line. Make multiple at the same time, stuff like that. So that's why we went to this typedef thing that will replace like all this. It will replace the need to do the struct, and you can just down below you could do student hello for, and it just replaces the need to have struct out there. So it becomes a little simpler, a little easier to read, a little easier to pass data back and forth by using the typedef. Just for kind of completeness, you can technically do this. So you wouldn't need to do this. I find this to be a little excessive, as far as making it a little too confusing. I like to keep those on separate lines, but it is valid. And if you're only going to use it only going to make those variables that name, then that's perfectly fine. But if you're only going to make these variables out of this structure, and there's never going to be another use, you could technically do this as well. You don't need to name it. You can just go in with this. So this is the name of the structure. This is the name of the data types that are using that structure. You always need a semicolon at the end, and that's about it for how to set things up. You can fill this with anything, including other structures, which we see right there. That's a structure inside a structure. All right, so perhaps too much information there to really get going, but will definitely help us out. So now we made a student called Chris. The student structure contains all this information in it, so if we want to access any of that information, we just do Chris, which is, our data variable, and then do the dot, and then this will grab a piece of data out of it. So in the past, not using structures, you would try to do like if you wanted to have a whole bunch of first names, you might do first name, and I've got 10 first names and they're all 100 characters, and then you try to like line everything up using, all right, location 5 first name, location 5 last name are the same. Kind of works, but a little better organization is to say, all right, let's go get student Chris's first name. Obviously in this case it's Chris. You need to use the string copy. In C, doesn't have a great ability to use strings, so that they're an extension. So because they're an extension, you can't just do this like you can in some other programming languages. You can't just put a string into where a string belongs. You have to use functions called like string copy to copy that string in. What will happen here is it will take each individual character and copy it over one by one, because right here this is essentially an array of characters, and you're trying to like put it into a location. It doesn't work. We don't have strings by default in C. So from there you can do last name. We're gonna say just person. Copy it into a string last name. This is probably easier to see. So credits earned, they've earned 20 credits. So you just do that little dot symbol to grab the credits earned integer out of this data type, and you can reuse it however you want once it's in there. So you can do a printf or anything like that. Quality points. Again, same type of thing. In that case, it's a float. We're not really using it any differently. And then I've got two functions that I made. First one is pass by reference, which is the most common for structures. So one of the cool features of structures is these are all data types just like you have integers. So integers, you don't need to pass them by reference. You can just pass them by value, and it will just make a copy of it, and then you can return it that way too. It will just make a copy back. So that's a great benefit of structures, is you don't need to pass by reference. So if you had like some large collection of well, I mean, even if just this first line, this string here, by default you'd have to pass it as by reference instead of by value. And if you pass it by reference, you have to do the the asterisk and the ampersand to make sure it passes. Well, you don't need to use the ampersand in this case because it's already an address, but you need to use the asterisk, and that can be confusing to students. So to get around that, you could technically pass this entire thing just by value, and your function below would get a copy of it. So very convenient for like introductory programming to use structures, because you don't need to do the pass by reference, pass by value stuff. But the problem is it's really not that efficient for memory usage, because usually when you have a structure, it's a large collection of information. So I mean, here we've got 200 characters, 201 characters, 2 integers, and 4 floats if you include the floats that are in here as well. And that's a lot of information to copy each time you want to do something on this structure. So most of the time we're going to pass by reference, just so that we don't need to copy all this data back and forth. But should you need a scenario that I want to pass something by value, and it's a large collection of information, maybe in an array, and you want to figure out how to pass an array by value, you can technically just put the array inside a structure, and then you can pass the structure by value at that point. So in this case, yeah, I'm passing 1 by reference, 1 by value. We'll go down to the code that does this. So we'll start with the by value one first, which is right here. So we just can say student, current student. Technically, you can like return a student over here as well, just by saying student. Same as int instead of a void. This could just be student over here. I'll show you what it would look like. So in this case, I could just return a structure called student. You got student name, and then a couple, strings. You just say current student first name. So very similar to what you saw above, where we did the assignment, but here we're, grabbing the data back out. But hopefully this all looks familiar. You got, quality points. Doing little typecasting here to make sure that we're not dividing by an integer. That's about it. So print off the float, and it should print off the name and the GPA. In this case, it's not using some of the other information in there, which is why passing by value isn't that great again, is because every time you're going to pass this entire container of information that you might not need. So there's a lot of perhaps wasted copying for functions that aren't going to use everything about this student. Pass by reference. Up there we just pass the address to it. So we do a little asterisk, just like we've always done for passing by reference. And there it is. So normally when you pass by reference and you want to like assign something to it, like if we wanted to change the credits attempted, you would do something like this. So similar to if it was an integer, you would just do the asterisk in front and then set it equal to a value. In this case, you put the asterisk in front, and then you can grab out what's inside of it after you do the asterisk by doing the dot. So hopefully that looks similar enough to what you've done before right here, and then everything else after it just follows what you've learned from structures right in this video. So for whatever reason, we didn't really like the format of that, and it became a more and more needed thing to just have something that looked a little prettier. So in this case, these two lines mean the same thing. So we've replaced the asterisk in front and the dot in between with just an arrow, which means I've got a structure pointer, and I want to grab something out of that structure pointer. I will use the arrow. So interchangeable. Most of the time we're using the arrow. You'll see the arrow also in programming languages that have classes. The arrows kind of become the way to grab information out of a structure or a class that has a pointer. If you don't know what a class is, that's perfectly fine. You'll perhaps learn later in life. So I guess we can say, so billing info inside of this also has some information in it. So let's take a look real quick. Current student, billing info, and then we want to grab something out of billing info inside there. We'll grab amount owed. Once you do this dereference, the pointer and all that, through the use of either the asterisk and the period, you don't need to do that again. So once you're inside this structure, there's no more needing to use the asterisk or the arrow if you go internal to another structure. So let's say they owe $1,000. You can just do it this way. You wouldn't put the arrow here because that's not where you're dereferencing from. You don't do that. You don't have a double arrow. It looks like this. So none of this is part of this example, so we'll just get rid of that. But now these two chunks of code look the same, other than the function name, obviously. But we've got the asterisk up here to say that we're passing by reference, and then we've replaced the dots below with the arrows up here, and that's the only thing that's changed. So you can You can see hopefully that it becomes an easier solution. You just need to know that you need the asterisk and the ampersand. Hopefully you're out to the level that you know how to do those things. And then once you do that, anytime you have a structure by reference and you want to use it, you use the arrow. Anytime you have a structure by value and you want to do something with the data, use the period. Yeah, so you can see down here in part 1 of the output down at the bottom here. You can see Chris person 3.0. So same output from both those functions as expected. So that covers all that stuff right there. Part 2 is more useful. I mean, making a student called Chris doesn't really, I mean, that's not really portable code. Doesn't really do much. So more likely you're going to make a student array. So in this case, I made a class of 20, 30, and then I gave them a class size of 100. Mostly I limited to a class size of 100 because if you get into really large chunks of data, you're going to be doing something totally different. But maybe for a class size of 100, you might still like use structures to organize things. So same type of thing. If you want to copy a name, you have to go out and do the string copy function. And inside this, we've got class size of 20, 30. We grab the 10th student, which is the the 11th element in the array because we started counting at 0. And then same structure after that. Reuse the word structure, same format after that. So you replace Chris with everything in the past example with just class of 20, 30, and then location 10. You can still pass by a reference by grabbing that location, then doing the ampersand, and then you can still pass by value by sending it the 10th element. You'll make a copy of that and send it down. And if we look here, we get all that stuff again. Maybe it'd be good to, make part 2 look a little different than part 1. So we'll run that again. Part 2, Chris has a slightly higher GPA in that case, just to show that it is different between part 1 and part 2. All right. So hopefully that's all making sense. We're going to dig a little deeper into what's going on in the memory in part 3. So way up top here, we initialize some variables. We initialized an integer array of max values. Max values is set to 10. And then we set a pointer to an array. So array itself acts as a pointer a little bit, but the way C does it underneath the hood is a little different than a pointer. So we'll see that by setting a pointer to an array. So technically, and once we do this, pointer 3 will equal array 3. These become the same arrays essentially when you're manipulating the data. So we'll take a look into that. I also make a new structure called example 3. Example 3 is a typedef structure, so similar to our student. And then in here we have 10 integers followed by 100 characters. Example 2 done without the typedef structure is the same format, 10 integers followed by 100 characters. And then up here in structure 1, we also have 10 integers, but in this case we wrote out all their names instead of having them in an array, followed by 100 characters. Also follows the example 2 format. So we've got 3 structures. They all contain the same chunk of data, but that chunk of data is in a slightly different format perhaps, and also we also use the typedef for example 3, which is what we make new structure out of. So saying, hey, we can do it this way or this way as well, just so you see those examples right there on 65 and 66. Okay, so For part 3, we're going to print out the address of the pointer that we just made. So pointer again is set to the location of the array. We're going to find the pointer of array itself. We're going to find out the address of array. We're going to find out the address of location 1. So go get location 1, then give me the address. And you can also find the address doing this. With the +2, this will give us location 2. Because C already knows that the array is a bunch of integers, it will count up the addresses appropriately. So if we look at what we have here, the address to the pointer is C8B8 at the very end there. And then the address of the array is C8C0. So very similar, they're about in the same spot of memory, but they are different. If we scroll down on the output, we see that the address of the array and the address of array location 0 are the same, which, like if you think about pointers, the pointer to the first spot should be, the pointer to the array and the pointer to the first spot probably shouldn't be exactly the same. Like you see here, the pointer contains the address. Like if you go and look inside this piece of memory at this location, it will have this address. In this case, C cheats a little bit and has the array pointer essentially just automatically default to location 0. So I'm not sure if you quite followed that, but just showing that in case you're the next level up of trying to think through these things. So the pointer actually contains the address of array 0, but it's at location this, and then you can see that each one is getting counted up by 4. An integer data type is 32 bits in the system, so that's 4 bytes of data. So each one goes up by 4, and the system knows it goes up by 4 because of the data type, which is why this +2 works, and also why the 1 technically works as well. All right, so down here we do a bunch of different assignments. So your normal assignment of array 3 equals 20. There you go. That's pretty standard. Here we're just saying, all right, go and input 124 into the array. Like if we use pointer here, this would not work because they aren't at the same address kind of thing. But in this case, 120, the first location of the array is location 0, so it will equal 1, 2, 3, 4. Probably don't do this, but worth showing as an example. We can typecast array into a structure, and we're just doing this to show that structures and arrays kind of keep memory in the same kind of order, and we'll see this over here. But we just found out that, hey, array without any pluses is the same as array 0, and we have all these memory locations that we had in there, and we put 1, 2, 3, 4 into that location. If we typecast this memory, if we typecast array into a structure, again, we just have 10 integers in a row, and that's how our structure starts off as well. So if we typecast it in there, we can get out individual elements of this structure one by one by going and saying, all right, give me example, and then 0 through 9 out of that location. So the way memory is organized for both structures and arrays are essentially the same. It just goes in order and just finds space for it. So if you treated them if you typecast them between back and forth, you'll see that they behave, how you would expect if you just, didn't even have a typecast there. So now we take an array, we typecast it into a example structure, a pointer to that example structure, because again, this is essentially a pointer for array. And then we use the arrow thing to get the element 4 out, and then from there we can assign 40 to it. And there you go. We can do the same thing with 5, but in this case we're doing the the asterisk dot format that we talked about, and that will allow us to set something into 140. So example structure had all these names in it, so that's what we were using. Example 2 and example 3 structure has an array, so very similar to what this array is. It's basically going to be exactly lined up to that array. So but we can take array, typecast it into a structure 2, go and grab the array out of that structure 2, and then go to location 8 and assign to 888. Works. You can also typecast it to this example 3 that was defined by typedef and set location 9 to 999. So a variety of ways. You're not going to really use these, so if you got a little lost in there, that's pretty fine. Pretty non-standard ways to do it, or advanced ways to do it. For the most part, you're not going to typecast between, from an array to a structure, just showing you in memory that everything lines up, and hopefully solving a little bit of that memory, how data actually exists question. So to print things out, you've gotten hopefully fairly good with doing a for loop, where you can just loop through your array and just print it out, and that's what we just looked at. This is all the printout from line 143. Works great if you have a collection of data that is not, you don't care what a certain location is. So if you just collected a bunch of measurements and you said, all right, measurement 0 through 9 are these values, works great to have an array like this. But where structures come in is if you have a collection of data that has a specific item. So x, y, and z are coordinates. You might just assume that there's 0, 1, and 2 in your array, but that's pretty rough. And then if you wanted to attach like a scaling vector, or a scaling number, or a direction to that, then you'd add more elements to your array, and they wouldn't really necessarily correlate to location 5 is my scaling, or my magnitude, or my speed, or whatever you wanted to attach to this grouping. So you might do it, and you might make your program work if you're programming constantly over a few days. But if you go back and look at it later, you're like, okay, why am I trying to manipulate location 5 here in this array? What does that do for me? And if you give your code to someone else to work with or modify, then they definitely don't know what it is. You might have like great comments, but if someone's reading your comments constantly, they're probably pretty confused. So we try to make our code as readable as possible, which is where structures come in. And you can, like, right here, 0, 1, 2, and 3 don't really mean much, but if this was like student information, GPA, class name, names, stuff like that, that's where we're going to grab out, individual elements and able to manipulate them. So not as easy to print out, obviously, but in this case we can say value at location 3 is 3. So you might say last name of student is last name. So by naming things in our code, it helps with readability, helps with organization, helps us not make mistakes by accidentally grabbing location 4 instead of 5 and taking forever trying to debug that. Structures provide the structure that you need to write solid programs. Again, all this is just typecasting the array into our structure example, grabbing all these locations out and then printing them out. And if you look, if we do that, all the data perfectly matches what we saw when we just went through the integer list. So part 4, we went through new structure just to show you can just go and write to a location in new structure. So new struct, again, that was an example 3 structure that we defined way at the top right here. So an example 3 new structure, and we can go into structure array, write to location 3, which is element 4, and we assign 5 to that. You can do a string copy into this using hello. These things work. So this is kind of your standard way that you'd use structures. Everything after this is, again, just diving deeper into what you can do. So if we go in and we print off everything in this, so in this case we're gonna typecast our structure, grab the address of it, typecast it into an integer array, which is what a pointer to integers is, and then we go to location 0. In this case, we're going to go, instead of 0 to 9, we're going to go 0 to 15, because we want to look at the elements, the data beyond our integers. So line 184 here is what prints out all this stuff. We see our 5 at location 3, so everything's working. These elements technically could be zeros and technically something else. Most of the time when I run this program, they actually are not zeros, because other data could have existed there in the past, and since we didn't overwrite it, it could be anything. And then location 10 doesn't make as much sense. And if we look at location 10, what would location 10 possibly be? We go up and we look at what is example 3. Example 3 has 10 integers followed by 100 characters. So location 10 is the first character, or at least the address of the first character. So 10, 11, 12, 13, 14, 15, don't really know what exists there. Apparently there's some data at 10 and 11. Some interesting data here. Let's see, we've got 181, 9043, 144. So location 10 so it contains that decimal value, which exists as this hexadecimal value once I do the conversion. So you're like, well, that's a giant number there. But once we're over in hexadecimal land, we can convert things like you can go to ASCIItable.com or look up your ASCII table, and we take up 48 and hex 48 is an H, and hex 65 is, what do we got for 65 in hex? Just make sure I did it right, lowercase e. So location 0 in memory, location 1 in memory, location 2, location 3, which pretty much implies that I'm not going to look it up, but pretty good confidence that lowercase l for these two. So again, this number right here is decimal value, which equals that, and so Least significant would be the lowest address level, which contains 48, and then 65, and then 60, 68, 6C, and then 6C. So if we went and grabbed like the address of each of these individual ones, we would see that it's only counting by 1 for all these instead of by 4 like we saw earlier. So if you remember, each one of these array locations counts by 4 because they're 32-bit numbers. Characters are only 8 bits, so we only need to count by 1 each time. And when we interpret the data, we only want to interpret it as 1 byte instead of 4 bytes. So this is what it looks like when it's 4 bytes. Here in hex, we can start to see that, hey, there's a little bit of a pattern. That's where we go and decode that pattern into hexadecimal numbers and say, hey, this happens to align with what we learned here. So if we wanted to like extract this out in code, we could take our structure and typecast it again just like we did before. We're going to go to location 10, which is where this started to devolve. Grab the location of address 10. Address 10 is this number, but this number starts way down here in the address land. Turn that address into a character pointer instead of an integer pointer, so now it's only going to count by 1 location each time, and it's going to treat everything as 8 bits, and then we can start going through as a character 1 by 1 to see what that looks like. So location 10 pointer plus 0, and then we can actually grab out each individual character from our structure. So just to show how it exists in memory, that structure contains 10 integers followed by 100 characters, and there's nothing else in there. So you can go and grab out anything you wanted to if you wanted to. This is way uglier than just grabbing it out using the structure format, but it all does exist in that structure. And if you wanted to do a copy, it would take all that information and then copy it to a different point in memory and then send that to the function. All right. So let's see. Oh yeah, you can still print them out. Did it a little bit of the normal way right here. So if you want to get location 0, you can just get location 0. Nothing too fancy here. This is all using the typecast over to example instead of example 3. So you can typecast or whatever you want to between structures as well. And then at the very end, I say, all right, if I just want to get if I want to get it as example 2, I can get it example 2. I'll just typecast it over and then use my arrow. If I want to get it as an example, I can typecast it over and then use the arrow. And then here, if I just want to treat it as an example 3, it is in a pointer, so I can just use the dot in that case. If you really wanted to, you could go and like turn it into an address and then get it out like that as well. No one really does that, just making sure that you can see that all 3 of these are essentially the same format. Don't need to use this format here because by default it's not a pointer. So a lot of things. Hopefully you can pause and process what's going on in here, but takes you about as far as you'll really ever need to go for structures unless you get like seriously into programming. So we talked about memory, we talked about how to manipulate data, but yeah, for the most part, when you're doing structures, you're going to be in this world right here. Line 34 through 50, you'll treat functions like 52, probably not 53 too much, because again, we don't want to make copies of all our data. So this is our standard way of operating, and if that plus this kind of stuff and this kind of stuff, and the functions at the bottom make sense to you, you're doing great. This, if it's starting to make sense, then awesome. You're well on your way to understanding the lower levels that might help out with understanding of other things. But if you want your basic level of structure understanding, you want part 1 and part 2 to make sense. 3 and 4 probably will take some time. If it's already making sense, then great. You're doing great.